Alright, so now we're going to go on to the analytical method for evaluating limits. The analytical method is the favored choice for methods in evaluating limits. It is the most reliable, and it's what everyone uses if possible. So let's go back to our original example. The limit as x approaches 1 of x squared plus x minus 2 over x minus 1. So remember, we were calling this expression f of x. F of x is x squared plus x minus 2 over x minus 1. Well, what we can do is we can factor this expression. The numerator can be factored into x plus 2 and x minus 1, or x plus 2 times x minus 1. Now, the algebraist in you is probably clamoring to cancel the x minus 1s, and that's a good thought. This function, well, I'm going to write something that's not quite true, but then we're going to fix it up. This expression is almost identically equal to this expression, but there's a difference. This function is not defined when x equals 1, whereas this one is. So these two expressions are not exactly equal. So here's what we need to do. We need to put in the stipulation or proviso that x is not equal to 1. So how does the function f compare to the function g defined by x plus 2? Well, they are equal except at one point. This function is not defined when x equals 1, and this one was, and so we had to, in order to make them equal, we had to put this in. We had to stipulate that x not be allowed to be 1. So, let me show you how we're going to use the analytical method and this factoring that we just used, or that we just observed. Remember that when we're evaluating this limit, we are not going to let x go all the way to 1. So what happens at x equals 1 is really immaterial. Alright, so if we're looking at the limit as x approaches 1 of x squared plus x minus 2 over x minus 1, well, the first thing I did was I factored this function. So this function and this function are exactly the same. This is exactly equal to this because the functions are the same, and we're looking at the limit as x goes to 1 here and the limit as x goes to 1 here. But when I go from this line to this line, I have made a change. This function is not equal to this function. But that's okay. Why is it okay? Well, these two functions are the same except at x equals 1. Well, we're not really interested in what happens at x equals 1, just as x is close to 1. So if we're looking at a value of x that's close to 1 but not equal to 1, then this and this are going to have the same value. These two expressions are going to have the same value. I'll draw you a picture in just a moment that I think will maybe shed some light on what's going on. But anyway, so this limit as x approaches 1 of x plus 2 times x minus 1 over x minus 1 is equal to the limit as x approaches 1 of x plus 2. I'm really just ignoring these x minus 1s. I'm simplifying this. And then now, if we substituted in 1 here, we got something that was undefined. We got 0 over 0. But if we substitute in 1 here, we get 3. 1 plus 2 equals 3. Alright. So note that we use the limit notation. This is something about notation. we kept the limit notation all the way to here. It wasn't until we actually substituted in a value for x that we dropped the limit notation. This is a number. It is the number 3. If we had left off that notation, then what we'd have was a function, and it doesn't take on any particular value. So without the limit notation, we're talking about just a function. But with the limit notation, in this particular case, we are talking about a number, and the number happens to be 3. So anyway, you keep that limit notation until you get down to the stage or the step where you actually substitute a value in, and that's when you drop the limit notation. Okay. Can we do another one of these? Can we take a look at the limit of x minus limit as x approaches 4 of the quantity x squared minus 16 over the quantity x squared minus 4x? If you substitute in 4 for each value of x, you're going in the numerator you're going to get 16 minus 16, that's 0, and in the denominator you're going to get 16 minus 16, or 0 again. We're getting 0 over 0. Now that does not mean that the limit is undefined. The function is undefined at 4, but the function might be such that so well behaved that as the x's get closer to 4, that the y values get closer to something. All right, so can we factor this function in a way that will be helpful? Well, the numerator is a difference of 2 squares. It's x minus 4 times x plus 4. And then the denominator has a common factor of x between the two terms. So I'll factor that out, and that will leave x minus 4. Now, this function and this function are exactly the same. Now, is this function the same as, well, let's cancel. Is this function the same as this function? The answer is no. This function's not defined when x equals 4, but this one is. But remember, we don't really care what happens as x. We care what happens as x approaches 4, but we don't care what happens at x equals 4. So you may be wondering, well, isn't the next thing we do to actually substitute the 4 in? Yes, it is. And if we do, we get the number 2. And so this limit is 2. Alright, so let's take a look at our first example in a little bit more detail. I want to look at a graph of that. I think you can see what's going on if you find all this confusing. Alright, so our function, let's go back. So we're looking at this example. We looked at this function and then we compared it to x plus 2. Remember, we factored the function and then took out the common factors. So this function and this function look an awful lot alike. The only difference is that this function is not defined when x equals 2, whereas this function is, when x equals 1, and this function is defined when x equals 1. Okay, so what have I just drawn? Here's 1, here's 3. Here's the function f of x equals x squared plus x minus 2 over x minus 1. How do I know that's the graph? Well, To be honest, what I did was I graphed x plus 2. Remember that this function, x squared plus x minus 2 over x minus 1, is identically equal to the function x plus 2 as long as we stipulate that x is not allowed to be 1. So what I did was I drew the graph of x plus 2, so it's a line of slope 1, y-intercept 2. But then when I got to x equals 1, I just omitted that point. So when I'm looking at the graph, when I'm looking at the limit of this function as x approaches 1, remember, I'm not letting x go all the way to 1. I'm not really interested in what happens when x equals 1. So what I do is I replace this function with this function, kind of ignoring that part. What I'm doing by replacing this function with this function is I'm filling in that point. But by filling in that point, I have not changed the limit. The limit of this function as x approaches 1 is 3. The limit of the original function I had here, where you had the open circle, that's also 3. Because as x approaches 1 from each side, the y value can be made as close to 3 as we like.